Hey everyone, this is the LiGrip O2 Green Valley's top tier SLAM LiDAR scanner. In today's video, I will be putting it through a full test to see how it stacks up against the competition. Even though the device is fairly large, it still fits into a compact cabin-sized hard case. The device comes with two batteries and a proprietary charger that uses a DC jack. That means you can't charge it with a regular USB-C cable, and you will need to remove the battery from the unit whenever you charge it. The base plate is made of plastic and includes markings for ground control point collection. The scanner weighs 2.2 kilograms, which is pretty standard for this type of LiDAR sensor. It also comes with a soft silicone sleeve to protect the lens. There is a lock lever you need to release before inserting the battery handle. Once it's locked in place, it's very secure with no movement at all. To remove the battery, unlock the lever, place the release button, and then slide the battery out. The LiGrip O2 is equipped with three 12 megapixels RGB photo cameras. Most LiDAR scanners only come with two cameras. It also includes two virtual SLAM video cameras, each with a 1.3 megapixel sensor. On the back, it has both a mechanical power switch and an operation switch, each with its own LED indicator. That means you can operate the scanner without needing to connect it to a phone. The RTK antenna comes pre-installed, and it looks like it can be removed. It feels sturdy and locks firmly in place with no play at all. On the side, there is a USB-C port for data transfer. Just plug it into your PC and it will show up as a drive. Transfer speeds are impressively fast, over 150 megabytes per second. It comes with 512 gigabytes of internal storage and is not expandable. Now let's move on to the most important feature on this scanner, the LiDAR sensor. This scanner is equipped with the Hesai XT32M, a top-of-the-line LiDAR sensor. It delivers a detection range of 300 meters and a scanning speed of 640,000 points per second. Although the sensor supports a 300-meter range, the scanner doesn't use the full distance for point cloud construction. By default, it's capped at 70 meters to ensure maximum precision is maintained. During scanning, the LiDAR sensor rotates a full 360 degrees, creating a spherical detection range. This means you won't have any blind spot at all. With this sensor angle, the LiDAR beams directly toward your feet, ensuring the entire floor area is captured without needing to tilt the scanner. I have used scanners with the Hesai XT32M sensor before. This sensor has a narrow 40-degree beam angle which produces sharp corners and very thin walls, but because of that narrow beam, orbiting is required to achieve full coverage. The LiGrip O2 is equipped with high-precision IMU sensors running at 200 Hz. According to the manufacturer, this ensures highly accurate floor-to-floor leveling. Back at the three-story house, I'll be testing the scanner's tracking performance on a very narrow walkway, as well as checking floor-to-floor leveling and wall-line parallelism. You can connect the scanner either through its own hotspot or let the scanner connect to your phone's hotspot when using the RTK function. For this scanner, the scanning mode must be selected before starting. In this test, I'll be using the indoor mode. As with all SLAM LiDAR scanners, you need to place the unit on a steady, level floor during initialization. One drawback I have to point out is the phone holder. It's a clunky plastic mount which really feels out of place on a scanner at this price point. Speaking of price, I have asked Green Valley 3 times, but they still haven't disclosed it. Based on my estimation, this scanner should cost somewhere between 15 to 17,000 US dollar. With this class of IMU sensor, I can complete the entire scan walking forward, just as I did with the Manifold Tech Pocket 2. This type of SLAM LiDAR requires virtually no skill to operate. With SHARE and FJD scanners, you still need some skill and proper scanning technique to operate them effectively. My second complaint is about the mobile app. Pan and zoom with finger gesture are so difficult that I eventually stopped trying altogether. Fortunately, the orbiting LiDAR head provides complete coverage with no blind spot, so you don't need to rely heavily on the screen during scanning. The mobile app doesn't display walking speed, travel distance, or any indicator of tracking quality. However, it's surprisingly difficult to get a failed scan with this device. The IMU sensor performs so well that producing an error is rare. In just a minute, we will see the scan quality, and you will notice the clear difference between this LiDAR sensor and the Livebox 360 sensors. As with all SLAM LiDAR system, a loopback is necessary to correct accumulated errors. Green Valley's post-processing software is called LiDAR 360 MLS. Unfortunately, its interface looks dated, almost like something from the 1990s. The layout isn't intuitive and often feels confusing to use. But the final result tells a different story. After processing, the software generates an accuracy error report, something you won't find with any other LiDAR scanner. The processing time took about 33.6 minutes, roughly twice as fast as the SHARE scanner. The LiDAR range is capped at 70 meters, and the operator position is cropped out within a 0.8 meters radius. And here's the accuracy error heat map. This scan shows entirely blue, which indicates it achieved the highest level of accuracy. 99% of the scan falls within a centimeter accuracy error range. Here are the flattened photos from the 3 cameras combined. Together they produce roughly 20 megapixels resolution, which is fair for a scanner released in 2025. The scan data is output into 2 separate files, but they can later be combined to one dataset. It can capture fine details even 64 meters away, something the Pocket 2 failed to detect when I performed the same scan just a few days ago. And this is the cleanest scan I have ever seen from a SLAM LiDAR scanner. The flaws are perfectly level on both the second and the third levels. I may need to import the data into BricsCAD to verify the error. The wide side of the house is also perfectly level across all floors. Here in BricsCAD, I tested the color mapping accuracy using a 1.2 meter wide ceiling board. The result read exactly 1.2 meters, confirming that the color mapping accuracy is excellent. I'm checking wall parallelism using the offset command, and the walls are perfectly parallel. I can't detect even the slightest misalignment. This is the third floor bathroom, the most difficult room in this house for a SLAM LiDAR scanner. Most scanners would show slight misalignment here, but I truly can't detect any error. And when I switch the point cloud into a vibrant colors for line tracing, its quality really shows. The wall lines are incredibly thin, most measuring only about 5 millimeters. If no one told me, I would have assumed this scanner came from a terrestrial LiDAR scanner. On the second floor as well, the wall lines are the sharpest and the cleanest I have seen. And the parallelism is excellent. The wall remains perfectly aligned without any detectable deviation. The wall orthogonality is also excellent. The intersections are precise and the angle holds true. Now I'm verifying the floor-to-floor levels using the offset line, and they align perfectly without any detectable error on both the second and the third floors. All the tests I perform here is the essential quality for the 3D scan data for accurate building model in CAD. Scan data from the SHARE Pocket 2 and Trion P2 can also be used to produce building models, but they won't reach the same level of accuracy as the LiGrip O2. If I were to create a building model from this scan data, the error would be less than 5 millimeters, whereas with other scanners it could range from 10 to 20 millimeters. The upper scan was captured with the SHARE S20, while the lower one comes from the LiGrip O2. The price difference between these two scanners is significant, but here I just want to highlight the difference in the floor plan cross-section. You can clearly see the point cloud density and the near zero blind spot from the LiGrip O2. The wall lines are thinner with noticeably better parallelism. Looking at the wall corners, the LiGrip O2 produces much sharper and cleaner intersections. Here's the second floor, and here is the ground floor. Here's the comparison of the staircase cross-section. The LiGrip O2 produces a much sharper and more accurate profile than the SHARE S20. Since the staircase is only 90 centimeters wide, this level of detail simply can't be measured with the terrestrial LiDAR scanner. In the second test, I will demonstrate the scan feature most LiDAR users request, RTK Fusion. RTK Fusion is the feature that lets you begin scanning outdoors with RTK enabled, then move indoors for SLAM-based scanning. The software automatically weights the trajectories from both RTK and SLAM, selecting whichever delivers the highest accuracy. Now I'm moving indoors and soon I will lose GPS reception. I perform exactly the same scan as before, covering all 3 floors. Since about 90% of the scan is indoor, this will clearly demonstrate how RTK Fusion handles the transition from outdoor RTK to the indoor SLAM. When coming back outdoors, all I need to do is wait for the RTK to regain a fixed solution, then walk back to close the loop. After processing, the scan data is aligned to the true north, and each point in the cloud carries GPS coordinates. After inspection, the scan data come out just as good as a SLAM loop scan with consistent floor-to-floor leveling. When I drop the scan data into BricsCAD and turn on the street map, the alignment matches perfectly. This is how you achieve an interior scan with georeference, and it's essential for architectural design. For the accuracy test, I will walk a 100-meter loop without RTK, then measure a known 30-meter distance to verify the accuracy error. It seems like the LiGrip O2 doesn't perform well in this environment. In areas further from the walls, it produced noticeably higher accuracy error. About 66% of the area shows an accuracy error in the range of 1 to 3 centimeters. When I measure the known 30-meter distance, the scan reads 30.005 meters, about 6 millimeters of error. Next, I will scan a larger loop, 560 meters long, without RTK, and then verify the accuracy error against a known 30-meter reference. This time, the LiGrip O2 reports excellent accuracy. 99.88% of the data falls under 1 centimeter. Let's see if that consistency holds. When I measured the known 30-meter distance, it came out as 30.025 meters, about 25 millimeters of error. That's above 1 centimeter accuracy reported by the software, showing the report isn't entirely reliable. Next is the 10,000 square meter shopping mall scan. This is my current testing site with over 700 meters of trajectory across a wide area, ideal for evaluating capture range. On the left, there is a tall building constructed with a post-tension slab system, which has highly accurate column spacing, making it a perfect reference for checking scan accuracy. This scan includes both outdoor and indoor area in a single session. And here's the scan trajectories. I also went up the second floor of the shop area. This scan is 900 meters long, and it took about 1 hour to process the data. The report shows 99.58% of the area under 1 centimeter of accuracy error, but as we have already seen, those reports aren't entirely reliable. So I imported the scan data into BricsCAD and measured the precision of the column spacing. Those 4 column spans show only 4 millimeters of maximum deviation, which is impressively accurate. You can't achieve this result with a total station since it measures point by point. Here, the measurement is captured from a continuous line. When I measure the orthogonal, it reads 90.415 degrees, the same value I recorded with the Pocket 2 a few days ago. When I measure the orthogonal of this concrete slab, it reads 89.988 degrees, only 0.012 degrees from a perfect right angle. The second and first floors are also perfectly level with no detectable deviation. The overall colorized point cloud quality is outstanding, low noise with sharp corners. Now I'm going to compare the LiGrip O2 with the best Lightbox 360 based scanner I have, the Pocket 2. The top of the signboard wasn't captured with the Pocket 2. This confirms the LiGrip O2's longer detection range, and the O2 also delivers better color resolution. Here, the Pocket 2 produces better color resolution than the S20. In this case, the O2 remains the top performer, producing a denser and noise-free point cloud. And again, the Pocket 2 produces better colorized point clouds than the S20. In this picture, the difference is significant. And again, the Pocket 2 performs better than the S20. But in this case, the O2 and the Pocket 2 perform equally well. The S20 also performs similarly to the Pocket 2. On this perspective view, the O2 captures more of the ground area. And here with the S20, this review video is quite long, but these devices are expensive and I want you to have as much information as possible before making a purchase. As with all the videos on this channel, I never ask manufacturer for compensation or to keep the devices, and I don't earn any commission from their product sales. Because Green Valley never disclosed the selling price, even after I asked multiple times, I estimate it will likely fall around 15,000 US$. For the 100-meter loop accuracy test, the O2 recorded an error of just 6 mm. For the 560-meter loop test, the O2 performed the best in this chart with just 25 mm of accuracy error. With high precision IMU sensors, the scanner requires no special skill to operate. Just like the Pocket 2, its tracking performance is excellent. And for the floor-to-floor level, it delivers the lowest and undetectable deviation, leaving all the competitors behind. As we saw, the O2 produces the best colorized point cloud I have ever seen from a SLAM LiDAR scanner. The wall lines are extremely thin, sharp, and low noise, measuring just 5 mm in thickness. Its color mapping also stands out with excellent resolution and accuracy. The mobile app on the O2 feels outdated. It cannot produce a true colorized preview point cloud, and it's impossible to orbit or pan to inspect the scan data. The information display is also quite limited. There is no speed, no distance, and no RTK quality indicator. The software license on the O2 is locked, but it can be moved from one PC to another without needing to contact the support. Point cloud processing time is decent, about as fast as SHARE with its latest update, though still not as fast as FJD. The Green Valley's PC software has a user interface that looks like it's from the 1990s, and it isn't intuitive to use. One major drawback of the O2 is its GPS reception. It's not as strong as the SHARE S20. In areas where the SHARE can lock onto more than 35 satellites, the O2 only manages around 20, and it loses fixed solution very easily. There is a 3D function in the software, but it's not major feature, so I didn't test it. The device comes with 512 GB of internal storage, but it's not expandable. This is the biggest feature we all want to see in every LiDAR scanner, RTK Fusion. The O2 performs flawlessly here, while the FJD scanner can also handle this task. It doesn't match the O2's level of performance. For reliability, it's still too early to judge. I have only completed 15 scans over the past 2 days. For technical support, Green Valley told me they would get in touch within 2 working days, which is absurdly long for a professional measuring tool. And finally, GCP coordinate extraction is supported, leaving SHARE as the only LiDAR scanner on the market that cannot perform this task. Here's my review on the Green Valley LiGrip O2, one of the best SLAM LiDAR scanner I have ever tested. Thanks you guys for watching. I'll see you in the next video.